You know, when we think about AI vision, we usually picture something pretty simple, right? Like just putting a label on a picture, cat, dog. But what happens when we need more than that? What if we need to know where an object is, its exact shape, or even predict what happens next? Today, we're going to dive into how AI goes way beyond just the label.
So you hear all the time about AI being used in medicine, especially for analyzing these incredibly complex volumetric data sets, like CT scans. A computer can look at hundreds of these individual slices, which all together make up a full 3D image of a patient's body.
Okay, but what does that really mean in practice? When we say an AI analyzes this scan, what is it actually doing? What kind of information can it possibly pull out of all this?
Well, for a long time, the main job for a convolutional neural network, or a CNN, was basically just classification. It would look at the entire 3D scan and then spit out a single label. It's a binary choice, a simple yes or no answer to a really specific question.
But here's the thing, right? A doctor needs way more than just a yes or no. They've got to know where the problem is, how big it is, and its exact characteristics. A single label just doesn't cut it.
And this right here, this is the massive leap we're talking about. On the left, you get a simple label, abnormal. Okay, useful, but limited. On the right, you get a detailed blueprint, and that blueprint is what we call a structured output. It's not just a single word. It's a whole set of organized data that gives us a much, much richer picture of what's going on.
All right, so let's grab the first tool from our advanced AI toolbox and see how this all starts to build. We're going to begin by figuring out not just what is in an image, but exactly where it is. So this first task is called object detection. And instead of just giving a thumbs up or thumbs down on the whole image, the network's job is to pinpoint the exact location of one or more objects inside it. So how does it do it? Well, it predicts what's called a bounding box. And you got to think of this less like a label and more like a set of instructions. The network actually outputs a vector of numbers, coordinates like its center point, and its dimensions like width, height, and depth that precisely define this box in 3D space.
Let's bring this back to our medical example, because this is where it gets incredibly useful. By drawing a bounding box around a specific organ, or maybe a tumor, the system can focus all of its computational power just on that important area. This makes any later analysis, like getting a really detailed shape, way more efficient by just ignoring all the irrelevant stuff around it.
Okay, so a box is great, but what if a box just isn't precise enough? I mean, organs and tumors, they're not perfect rectangles, right? So how do we capture their true, complex shapes?
This brings us to the next tool in our AI toolbox, Semantic Segmentation. And this is where it gets really cool. The network doesn't just draw a box around an object. It basically creates a perfect pixel-by-pixel stencil of it. Every single pixel in the image gets classified: liver, kidney, or just background.
And what's really powerful is how these different tools can all work together, like a team. The AI can start with a rough outline, a coarse segmentation, just to get its bearings. Then it uses that rough shape to draw a perfect bounding box, which efficiently isolates the area it needs for a final, super detailed analysis.
Okay, so we've seen how CNNs can understand the structure of an object in space. But what about structure across time? Well, it turns out this same core technology can actually be adapted to look into the future. Think about things like stock prices or weather patterns, data that unfolds over time. A CNN can actually be trained to spot the patterns in that data. The input is a sequence from the past, and the structured output is a whole new predicted sequence for the future. It's basically learning the rhythm of the data to guess what's coming next.
So you might be wondering, how on earth does one single type of network learn to do all these completely different things: draw boxes, create masks, predict the future? Well, the secret sauce is in how we set up the very end of the network, and critically, how we teach it.
The absolute key here is what we ask the final layer of the network to do. For classification, that last layer spits out probabilities for a fixed list of categories. But for a structured task, we change that final layer. We tell it to output a vector of continuous numbers, like the x, y, width, and height coordinates for a bounding box.
So to teach the network these new tricks, it needs a different kind of teacher. And in machine learning, we call this teacher a loss function. The loss function's job is simple. It looks at the network's prediction, compares it to the correct answer, what we call the ground truth, and tells the network how wrong it was.
So instead of just getting a score like right or wrong, the loss function is more like a guide in that game hot or cold. This formula, mean squared error, basically just measures the distance between the network's guess and the actual right answer. The whole training process is just the network trying over and over again to shrink that distance, to get its guess closer and closer until the error is tiny.
All right, so what's the big takeaway here? It's that convolutional neural networks are definitely not a one-trick pony. They are an incredibly versatile and powerful foundation you can build almost anything on top of.
It's all about changing their final layers and picking the right teacher, that loss function we talked about. By doing that, we can turn a simple classifier into a detector that finds an object's location, a segmenter that defines its precise shape, or even a forecaster that predicts a sequence of future events. It's an amazing, flexible toolbox for solving a huge range of complex problems.
So just think about that for a second. We've taught these networks to see not just what's in an image, but where it is, its exact shape, and maybe even what it's going to do next. Which leaves us with a pretty fascinating question for the future. As our own challenges get more and more complex, what new kinds of structures will we need to teach our machines to see?